Now it's recording, and it should be able to pick up my sound this time. Whereas the last lesson, it didn't. I think we're all good now. Okay, so let's, I'm not going to review or anything. There's really nothing to review. It's pretty simple stuff. So let's talk about another set of numbers. What do we use when we do a set? What's that crazy thing we put in front? A brace. It's not a bracket, it's a brace. A bracket would be this. That would be a bracket. And what would this be? A parenthesis. So these are brackets. Brackets and parentheses basically mean the same thing. And a brace could mean the same thing as well. But we specify sets using braces. Yes. Just practice. I practiced it. See, you start here, you go like this, you go out, and then you come back like that. All right. Sometimes they're good, sometimes they're bad. Depends on what kind of a rush I'm in. All right. So we are going to talk about prime numbers. So let's get rid of this and then write down prime numbers. And we're going to write a little definition and what prime numbers are. Everybody's heard of prime numbers, correct? Yeah. Now, whether we remember what they are might be a different story. Okay, so a prime number, first of all, they're in the set of natural numbers. So they are natural numbers, but they're not all the natural numbers. But they are. So what do we have to choose from? If prime numbers are the set of natural numbers, what do we have to choose from? What are the natural numbers? 1 and up, right? 1, 2, 3, 4, 5. No in-betweens, right? No fractions, no decimals, anything like that. Okay, so but they're natural numbers greater than 1. So 1 is not considered a prime number. Greater than 1. And are only divisible by 1 and itself. And I remember when I first learned this, the teacher would say that all the time. I'm like, I have no idea what you're talking about. You're saying all these words, and it's just bouncing off my head, falling onto the ground, and are divisible. Let's see. Only divisible by 1 and itself. Divisible by 1 and itself. So that means if you take a number and if the only thing that multiplies to get that number is 1 and the number itself, then it's a prime number. Okay? So let's think about them. So let's write this set of prime numbers. So it says it's greater than 1. So do we put 1 here? No, because it's got to be bigger than 1. All right, so what's the next natural number bigger than 1? 2. Let's see. Is there anything that multiplies to equal 2 except for 1 times 2? No, that's it. That's the only thing, right? What about 3? It's just 1 times 3, so it's a prime number, isn't it? Okay. What about 4? No, it's not prime. Why? Because 2 times 2 is also equal to 4, so it's not prime. Everybody got that? Yeah. What about the next one? 5. Is that prime? Yes. It is, because it's just 5 times 1, and that's it. There's nothing else. Okay? No natural numbers that multiply together to become 5. What about 6? Yeah. What about all the rest of the even numbers? No, because it's always what? 2. Right, if it's an even number, it's always 2 times something equals that number, correct? All right. Except for 2. 2 is the only even prime number. Everybody got that? Okay, because all the other numbers, 4, 6, 8, it's 2 times whatever, 2 times 4. So remember, a prime number can only be divided by, you can only take that number times 1. That's the only thing that equals that number. Does that make sense? Did that make any sense? Yeah. Okay, so 6 isn't. So 7. What about 7? Yes. Yeah, it's 7 times 1. That's the only thing, right? So 7. 8 isn't because it's even. What about 9? No. Why not? Because 3 times 3. That's right. Okay, 11? Yes. 12? No. 13? It's just 13 times 1. Well, no.
Wait, so 9's not 1.
Yeah, why did I put 9 there? Somebody stop me. Somebody did stop me. Thanks. I don't know why I put 9 there. I said it wasn't, and I still stuck it in the list. There we go. Yeah, I guess that would be confusing, Faith. So what about 15? Do I put 15 there?
No.
No, because 5 times 3. 16 not, because it's even. 17?
Yes.
That is prime, because it's only 17 times 1. That's it. And we could keep going forever and ever. Let's do a handful more. Okay, so 18, no. What about 19? Yes. What about 20? No. 21? 3 times 7, so no, it's not prime. 22 is not 23. Anything equal 23?
No.
No, it's just 23 times 1, right? And you get the idea now, don't you? So we'll just put a dot, dot, dot. We've kind of established a little pattern here, so we can put the dot, dot, dot. Now, could I just put like 2 dot, dot, dot? Would that be a pattern?
No.
Even if I put 2, 3 dot, dot, dot. Now, you really got to go, especially for primes, you really got to put a bunch so people can kind of see the pattern, okay, before you end up putting the dot, dot, dot. I don't know how many you need to put, but enough to follow a pattern. You can't just put 1 or 2 numbers and expect to be able to put a dot, dot, dot. Oops, see, I messed that one up. There you go. It's not the greatest, but those are prime numbers. It's the set of prime numbers, all right? What about the numbers that are not prime? We actually have a word for that. Anybody know off the top of their head if it's not prime? It starts with a C. It's nothing we talk about too much.
Common.
Composite. Okay, that's it right there. It's composite numbers. Okay, I don't need to write it down. You can write it down, though. It says there are all the natural numbers greater than 1 that are not prime. Okay, so it's basically starts off the same, but it's completely different at the end. Okay, they're just not prime numbers. Is -3 a composite number? No, because it has to be a natural number, which has to be greater than 1. So -3 is not a composite number. Everybody got that? All right, so let's start writing some composite numbers. Oops. See, now you got me thinking about drawing that brace, and now I'm doing terrible at it. All right, so it says it's got to be greater than 1, so we can't do 1. We can't do 2. We can't do 3, so 4. So basically, it's all the stuff that's not in here, right? So what do you got? 4. So all the even numbers except for 2 would be composite, right? Not 7. 8, yes, it's composite. 9, now we can put 9 in the list, all right, because 3 times 3, because it's not prime. 10 we could put on there. We can't put 11. We could put 12. So basically all the even numbers after 4. Let's do some more. Yeah, we could put we could put 14 in there, right? And then we could put 15. And we could put what? 16. We can't put 17. We could put 18. We can't put 19. We could put 20. We could put 21. All right, that's enough. We get the idea. So we put a little dot, dot, dot. And then there you go. Those are all the composite numbers. This is just vocabulary, right? It's not real math or anything. It's just vocabulary. So somebody talks about the prime numbers. Because we will talk about factoring prime, or we'll do prime factoring. Okay, we'll do things that are called prime factoring and things like that. So you need to know what prime numbers are if you're going to do stuff like that. Okay, let's talk a little graphing. Wow, I thought you guys would moan.
Okay,
See, there you go. That's what I was looking for. All right. Hopefully you'll like it better after this class because it's not as bad as what people think. And you're right. Most people say they groan when I say, okay, now let's do graphing. Everybody's like, oh, graphing. I hate graphing. All right. But it's really not that bad, especially these. Actually, you know what I should do? Oops. It does that every once in a while. I'm going to keep it right here so I can see the primes. So what I'm going to do is I'm going to graph all the prime numbers.
Oh, wait.
Okay? Yeah, it's just a little graph. It's no big deal. Eventually, we're going to be doing some more, actually fairly soon, I think. Again, I haven't taught out of this book. It's my first time teaching out of the book, so I just kind of skimmed through it a little bit. But they do graphing pretty early on, I think, even in the review chapter, this chapter 1, which is a review chapter. So this is our first one. It's pretty easy. So what I'm going to do is I'm going to graph all the prime numbers, all right? And we could do the same with composite. I've got it in my notes. I'm not going to do it because it's just all the other ones, right, that aren't on the primes. So what I'm going to do is I'm going to put some little lines here that represent these evenly spaced. They should be evenly spaced as much as possible. Just doing this by hand. So, but we'll say they're evenly spaced. Now I do have arrows on the end of this, but really, does it go in the left? Does it go to the left? No, it doesn't go to the left, does it? All right. So where does it start? The prime numbers. We're doing the primes. Starts with 2. All right. So what I'm going to do is this, though. I'm going to put a 1 here. Then I'm going to put a 2, 3, 4, 5. Now I'm not going to go all the way to 23. 9, 10, 11, 12, 13. Well, let's go to 4. Let's go to 15. I like 15. Count by 5s. Okay, so what we do, let's put a different color here just so it stands out a little bit. Let's go blue. All right. What we're going to do in order to graph it, we just put a dot on the little line, the up and down line, where that number is located. Okay. So what's the first dot I'm going to put? Where am I going to put it? On the 2. Pretty simple. All right. It's kind of baby stuff. Wouldn't you agree? I mean, you're starting off easy, right? Get the summer cobwebs out of your brain a little bit. Right. So, and then next one, we'll put a 3. Do we put a dot at 4? No, because it's not prime. We're only graphing the prime numbers. So we basically just put dots on all the primes. 5, then what? 7, and then we go all the way to 11, then we go to 13, and on this particular graph, that's it. Now this arrow indicates the same thing as the dot, dot, dot. It just means it keeps on going. Follows that pattern, and it just keeps on going. If I was to graph all the composite numbers, I would do the same exact graph. I'll tell you what, let's do this. We'll keep it on the same graph. I'll do it in this. Is that red or orange? Kind of looks red. All right, so let's put all the numbers that are not. So basically, all the non-blue ones, I'm going to put a dot, right? And that would be all the composite. So the composite would be what? It'd be red, but the numbers themselves would be 4, and then 6, and 8, 9, 10, 12, 14, 15. So everything's colored in, right? All the natural numbers. But the blue ones are all the prime, and the red ones are all the composite. All right, so that's it. Now I know you won't be able to go color-coded on your paper probably, unless you got a bunch of colored pens, but that's all we're going to do. All right, let's do this. Tell you what, let's just change colors instead of using. Oh, sorry, did I go too fast? All right, so all the primes are, in my case, all the primes are in blue and all the composite are in red. Everybody got that? Yeah, that's pretty easy. I'll just keep that there just so you can look at it. All right, let's talk about another set of numbers. We talked about integers. This is hardly even worth talking about, but I'm going to anyway. Let's talk about the even integers. All right, so we put a brace. This is the set of even integers. So we put a brace. Where does the even integer start? Does it?
0.
Does it?
0 is a even number.
It is. But is that where we start with the integers?
No, I start after 1.
After 1?
Yes.
Did we talk about integers yet?
No. Then we start in negative.
Let me see. Yeah, we did. We talked about negative. You started in the negatives. That's correct. Okay, that's what I was looking for. You actually started in the negatives. So what's the first negative number? Negative infinity. Exactly right. So what do we show in a set in the braces? The dot, dot, dot. Right. So we start off with the dot, dot, dot. That's what I was getting at. Everybody with me on that? And we just need some numbers to establish a pattern. I mean, if I wanted to, I could go like start at negative 25 and then work my way up. But that'd be silly, wouldn't it? It's kind of a waste of time. So let's just start. I'm going to put a comma here. So that's a comma. And let's just start with negative 3. Let's go to negative 2, negative 1. Are they all the integers? I put even integers. Let's do this. Let's just put the integers first, then we'll do the even. Sorry about that. Negative 3, negative 2, negative 1, and then what? 0, and then what? 1, 2, 3, dot, dot, dot. All right, and then there you go. I could do more. We will for the even integers. So now let's do the even, okay? Sorry about that. So now let's do the even integers. So we put the little brace thing here, dot, dot, dot. Let's go a little bit further back than negative 3, because we want to establish a little bit of a pattern here. So I don't know. Let's start with like negative 6, right? So what's the next even integer after negative 6? Negative 4, and then negative 2, and then what? 0, and then 2, 4, 6, comma, dot, 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 and then we can end it right there. Of course, the odds. It's almost a waste of time to do this, I think. I don't know. So the odd integers, dot, dot, dot. I don't know. Where do you want to start? Negative 7, negative 5, negative 3, negative 1, 0, 1, 3, 5, 7, comma, dot, dot, dot. And then there you go. Piece of cake, right? Yes. Time.
You still put 0 in the odd integers?
It's a good question. No, you don't. Thanks for that. So you're keeping me sharp.
Add-a-ball.
Yeah, 0 is considered even. So I got a little ahead of myself, didn't I? There you go. That's better. Those are the odd integers right there. Thanks for keeping me on track. I need that sometimes. Everybody good with that? Because it's every 2, right? So from 0 to 2 is 2 spaces. So from -1 to 1 is 2 places, right? If I went -1 to 0, that's only 1 place. So even just skip 1, odd just skip 1. So you have to skip the 0. Yeah. You can't wait 10 minutes?
Should we get out?
I don't know. When do we get out? I don't know.
I feel like 30 minutes.
12:15 we get out? You got your agenda book? Okay. Fill it out. Say where you're going, what time it is, and I'll sign it. 12:10? 12:10. Okay. Yeah, 15 didn't sound right. Okay. Now, we did the set thing, but in math they do a lot of weird stuff. They have certain ways. Hey, I'm up here. A little bathroom request shouldn't turn into that. Shh. So, in math they do a lot of weird things. Sometimes they use a lot of symbols to represent words instead of writing the word out all the time. By the time if you ever are a math major and you go to college, you're going to take in all these math classes, and after a while, it seems like you're not even writing real words. You're writing all these different symbols, and all these different symbols stand for something. So this is what one of those symbols. I thought I had a pen on me. Anybody got a pen on them real quick? Pencil or whatever?
What, right with it? No, I was.
All right, so we have a lot of symbols. So here's one of the weird math symbols. I kind of doubt that you've seen this before. Let's go this pink color. I've never heard this before until I read the book. But this stuff right there they call the roster method, R-O-S-T-E-R. Never heard that before. And I've never heard this next one. They call it the set builder notation. But let's write it down. This is what the book calls it. I've never heard called it this before, but the set builder. Maybe if I could spell it. Yeah, write this down. Sure. The set builder notation. That's what it's called. Right, that's what it's called. Right? I doubt I'll ever refer to it again. I don't know. I've never heard anybody call it that before. But in the book they do. They call it this. So here it is. It starts off with the brace. And then we put an X. I'm just going to write it out for you. And then you put a line. Just a vertical little line up and down like this. And then you might say something like this. Shoot. There's a button on my pen that I accidentally push, and every time I move it, whether I'm pressing on the tablet or not, it makes a mark on there, and I got to remember not to push that button anymore. So X is an integer. I'll probably do that 100 times though the rest of the year. It says this is X and then a line up and down, and then it says X is an integer. This is just an example. This is not really like a definition of this thing. Is an integer that can be divided by 2. It can be divided by 2. I'll tell you what it means in a second. I know it's weird. Just write it down, and then we'll talk about it. So basically, what's an even number? And an even number, or an even integer, is something that we can divide by 2, right? So that's basically... It didn't. Well, why not? There it is. Divided by 2. See, I got to get the summer cobwebs out of my head, too, so bear with me. So this right here, this little X right there, this is what we say. I'm going to put it in parentheses, or in quotation marks. We say... the set of all X, the set of all X, that's what that first X right there means, okay? We don't just say X line, X is an integer. We say the set of all X, and this line, this up and down line right there, that up and down line, it means such that. That's how we say it, such that. They use that in math a lot. Okay, this is the first time you've probably seen it, but that means such that. So it says the set of all x such that x, which means it's inside the set, is an integer that can be divided by 2. So if I wanted to write a set that this thing describes, I would basically write a set of even integers, wouldn't I? All right, so instead of writing even integers and writing all those numbers out, I could write it like this. This is a different way to write it. Okay, they call it set builder notation. So you build from this. They describe what you want to do, and really it's not that big of a deal. Okay, so don't get all worried about this. But that's the way that people say it. So when you see something like this, there's all kinds of things that you can put in here. It's not just an integer that can be divided by 2. There's a million things you could put in here. It's this part right here is the part that's a little different and the part that we want to understand. So the set of all x such that, and then blah, 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 whatever it tells you that x does. Okay? Does that make sense? It's kind of weird, but that's all that. All right. So that would be an example of all the even integers. Let's do another one. Let's write the rational numbers. So let's talk rational numbers. So what have we talked about so far? We've talked about whole numbers, what? Prime numbers, composite numbers, integers, odd integers, even integers, yep, all that kind of stuff, okay? So now what we're going to do is we're going to talk about things called rational numbers. And what in the world is the difference between a rational number and all the numbers that we've talked about before? Well, do you remember what we said about integers and natural numbers and whole numbers? We weren't talking about the numbers that were in between, right? We weren't talking about the decimals. We weren't talking about the fractions. So what do you think we're going to talk about now? So we didn't talk about the ones that are in between. Now we're going to talk about the numbers that are in between, right? Fractions and decimals. And look at this word rational. What word does it have in there? It's got ratio. And a ratio is basically a fraction. Okay, so if I had 3/4, what you're doing is you're comparing those two things to each other. 3 to 4. I don't know, I'm not much of a gambler. I'm not any kind of a gambler. I never gamble, but you'll see that in ratios all the time when they give the odds, right, of betting on a game or betting on a horse or a car or something like that. They give you it as a ratio. They say, oh, the odds are, 5 to 1, or they're whatever. You've heard that before, right? Sure. Okay, that's a ratio. Okay, and that's what a fraction is. You're comparing one number to another number. That's what a ratio is. So this is called a rational number. So this number 3/4 is not in my integer list. It's not in my natural number list. It's not in my whole number list. It's not in any list that we've done so far until now. So that would be considered a rational number. What if you stuck a negative in there? So what if you had like negative 13 over 17? What is that kind of number? Where would I put that? Would it be an integer? It's got a negative, right? Didn't we say negative integers have negatives?
No, because an integer can't be
It can't be in before or in between. It's not an integer. Now you can't be I guess you could be a rational integer because you could write an integer as a rational number, to tell you the truth. Let's do it. Come up with a integer that would also be a rational number. Actually, all of them are. Well, 3 over 4. Oh, is that right? Okay, yeah, it's just a ratio. Anytime you have a fraction or a decimal, because 3/4 can be written as a decimal, right? What's 3/4 as a decimal? 0.75. So that would also be considered a rational number. Got it? What about the number 12? Is that a rational number? Could be. I could do it like that. Now is it a rational number? Yeah. Okay, so I could still consider that a rational number, couldn't I? So even the integers, the natural numbers, the whole numbers, blah, 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 all those things we've talked about right there could also be considered rational numbers because we could always make it into a fraction.
So what would be a rational number?
Irrational numbers. And that's what we're going to get to. Do we do irrationals yet? Well, yeah, we do it at the end here. So it's a good question. And we will get into that. So basically, anything that can be written like this, A over B. But you have an exception, though. We'll put that exception in parentheses. You could take any number and write it as a fraction because you could always put it over 1. But there's something, I want you to think about this first. There's something that B cannot be equal to. It can be equal to A.
0.
It can't be 0. Very good. Okay, why can't it be 0?
Because then it wouldn't be anything.
That's right, because if, let's say 5. Okay, 5 divided by 0. What is that? Is it 0?
1.
Is it? Who's got a calculator handy? Anybody got a calculator with them? Stick it in a calculator. You don't have to have a fancy. Anything divided by 0 is 0? You sure about that?
It would come up as, they can't do it.
That's right. Undefined is what they. Well, we say undefined. It probably comes up as like syntax error or something like that on the
I thought
calculator.
anything divided by 0 was 0.
Is it? So let's do this.
That's why when you ask Siri to do it,
Look,
she says you have no phone.
I'm gonna put a question mark here. Okay. All right. So I've heard this a couple times already that 5 divided by or anything divided by 0 is 0. Let's go back a little bit. Let's go. I don't know. 12 divided by 3. What's that equal to? 4. Did you ever learn how to check to see if it was? Yeah. 4 times 3 should equal what? 12. If you did it right. Okay. What about this though? Do that check. Is 0 times 0 5? Is 0 times 0 any other number? No. Okay. So, right. So, can you do this? Did you do it in your calculator? What's it say in your calculator? Did you get the calculator out? Oh, I thought you were going to get your calculator out. Anybody else have a calculator? Real quick. 5 divided by 0, or any number divided by 0. I don't care what it is. It probably says, what's it say?
Error.
Probably says error, or sometimes they say syntax error, or whatever.
Anything divided by 0 is 0.
No, they never taught you that.
No, it's
I'm
undefined.
tripping?
Yep, you be tripping. So, but let's do this. Okay, so 0 times 0 is not 5. All right, that's right. There's no way that you can divide by 0 because there's nothing times 0. All right, settle down. I know this is exciting, but settle down. So watch. There's nothing times 0 that's going to equal another number except for 0. Do you agree? Now, I'll tell you the truth. I don't know what 0 divided by 0 is.
0?
It could be 0. It could be 1. I don't know. Or it's just not anything. I don't think you can do it, period. I don't know. There's people that mathematicians like write papers on stuff like this, but I'm not a mathematician, so I don't know. Anyway, you cannot divide by 0. All right? Everybody got that? But can you take 0 and divide it by another number?
Yes.
Yes. What is 0 divided by 5?
0.
That is 0. Let's check. Just like we did back in the day when you're in elementary school, right? You check to see if that was right. Let's check to see if this is right. So you take your answer, multiply it by the denominator. What's 0 times 5?
0.
It's 0. So that does work, doesn't it? So that works. This doesn't work. Okay, you cannot divide by 0. So with all that said, what do you think B cannot be equal to?
0.
0. So you'll see this quite a bit in math. You'll see some stuff in some fractions, but a lot of times they'll say, well, B can't be equal to 0. Right? Because then it wouldn't be a number and it wouldn't be a rational number. Okay? So as long as B is anything else, it could be negative, it could be a fraction itself. I mean, even the denominator could be a fraction. It could be a decimal. It just can't be 0. Yeah. A could equal 0, correct. Yeah, A could be any number at all. B could be any number at all except for one exception, and 0. Everybody got that? And you'll see that quite a bit. A lot of times they'll, especially in geometry sometimes, they'll have like theorems and postulates and stuff like that. And they'll have that something cannot be equal to 0. And kids look at it, they blow it off, they don't think it's a big deal. But it kind of is a big deal that this cannot be equal to 0. Time.
So can rational numbers be decimals?
Yes, right here. We said a rational number could be a decimal. Yeah, any of these numbers can be turned into decimals, okay? So like, what's that? Well, let's talk about an irrational number in a second. Let's do this.
Wait, the 5 over 0 would be rational.
What, this one?
No, the other one. 5 over 0.
It's not anything. It's not even. It's just undefined. It's nothing. Okay. It just can't. It can't do anything to it. Yellow. Let's use yellow. Did we use yellow yet? Can you read that all right? Yeah, that comes out pretty good. Okay, let's do. The question says, it's a little example. I think it's example 1, actually, if you have your book. Did you guys go to the office and get your RenWeb thing straightened out? You need to before I give the first homework. You need to if you don't have a book, okay? So make sure you do that. Make sure you know how to get on there. And make sure you know, and you've downloaded. Who's actually downloaded the book to either your phone or your computer or something? Okay, 1, 2, 3, 4. Need to do it. It's really not that big. It's a PDF. It's a fairly small PDF. I don't even think it's like a megabyte. I don't think. I have to look at it. It's pretty small. So you should be able to download it. So get rid of some stuff, all right, that you don't need. Make some room. Download it on your phone. Download it on your computer, your laptop, or whatever you got at home. Make sure we do that. How can I turn this into a rational number? Right now, it doesn't look like a rational number. How could I turn it into a rational number?
Put it over 1.
You could put it over 1. There's a bunch of other ways you could do it. There's actually an infinite number of ways you could do this. What's another easy way you could make this into a rational number? Negative 700, is that what you said?
No, 7, just 7.
Well, if it was just negative 7, then it would be considered an integer. We want to make it look like a rational number. An exponent? No, it's going to change the value of it. It still needs to equal negative 7. Still needs to equal negative 7. Say that again? It still needs to equal negative 7. Yeah. I want to rewrite this, but I want to rewrite it so it's a rational number, but it's got to still equal negative 7.
Oh.
What is it? Yeah, I can't put it over negative 1 because then it's not negative 7 anymore. It still has to be negative 7. It's pretty easy. After I show you, you're going to like, oh man, that was. Nah. I just want to write negative 7 so it doesn't look like negative 7, but it's equal to negative 7. How about this? I don't think you're getting me. Maybe I'm not asking it very well. Yes. Okay. There you go. Nah, see, I told you it would say that. No, it still has to be negative 7. So now, this looks like a rational number, right? Because it's a fraction, but it's still equal to negative 7. You understand why I could do this forever and ever? Yeah. Okay, so I could go negative 21 over 3, right? And I could keep going and going and going. I'm not going to. All right, so we've written this as a rational number. You could do it like this, or you could do it like this. There's an infinite number of ways you could answer that. Here's one. This is one that, I tell you what, I'll show you. Okay, that's a decimal, okay? How can I show it as a rational number, like a ratio, like a comparison of one thing to another? Do you know your decimal places? What are your decimal places?
Hundreds.
So if I took this and I moved it here, here, and then here, what would it be? How many?
Times 100.
It'd be what? 125 over. How many places do we move it? 1, 2, 3. So it's what down here?
300?
No. There's a 1. How many? 1,000. Very good.
Oh, every time
So
you add a zero.
it's a 0. One decimal place is a 0, right? So 1, 2, 3 decimal places, so 3 zeros. So that is now written as a rational number, isn't it? Now, if I took this and reduced it, I'm not going to for the sake of time, but if I reduced it, it actually reduces to 1 over 8. So try it in your calculator. Put 1 over 8 in your calculator, and you'll get 0.125. All right? So all 3 of these are rational numbers. Okay? Yep. Since you guys asked about irrational numbers, let's show you some examples. So I should have said this.
How do you spell irrational?
Irrational. Just put an IR in front of rational. Okay? So what about irrational numbers? All right. So basically, if your decimal does not repeat, then it's an irrational number. So for instance, 1/3. Is that rational or irrational?
Rational.
It's rational because what's the decimal? You should know this off the top of your head. What is the decimal for 1/3? 0.333, and it keeps on going, right? So it does repeat. Would you agree?
Mm-hmm.
If it stops like 0.125, that's rational. So if it repeats the same pattern over and over and over again, or it stops, it ends, then it's a rational number. If it does not repeat a pattern, and if it does not stop, then it's an irrational number. So, for instance, the square root of 2. If I took the square root of 2 and put it into a calculator, I would get 1.41. It starts looking like it's going to repeat, doesn't it? But if you start putting some more numbers after it, if you put this in the calculator, you get this. I don't have all these memorized. I'm just looking at my paper, 5, 6, 2, ... Does it look like it repeats the same pattern over and over and over again? No, it doesn't. So it's a what? It's an irrational number. There's another number you use in geometry all the time that's an irrational number. It's pi. All right? So pi is an irrational number. So we all know pi to be what? 3.14. And then it's 1, 5,
Yada yada.
9, yada, yada, yada. 2653.
That was pretty good.
I don't have all that memorized. I only have up to 9 memorized. But it doesn't stop. Okay, it goes ... I actually used to have a poster a long time ago, and it didn't go all the way around the room, but it went probably halfway around the room, maybe like 100 decimal places, something like that. But at the very end of it, it had a ... There was a couple times in there you might have had 1 or 2 numbers repeat, 2653, 3, and then it just never repeated that pattern. If it never repeats a pattern and it doesn't stop, then it's an irrational number. Every number that we've talked about are still real numbers. Every number we talked about is a real number. What did I say? Was it yesterday, day before? What did I say? There's real numbers and then there's imaginary numbers. Irrational numbers are not imaginary. They are real numbers. They actually are on the number line. Okay? But they're irrational because the decimal doesn't repeat. This does repeat, so it's rational. So if it doesn't repeat and it doesn't stop, then it's an irrational number. Everybody got it?
Yeah.
Okay. So we'll stop there. There's a little bit more to do before we get to the homework. Maybe we'll finish it tomorrow. Okay, that's it.